Welcome to the Week 2 Calculus Review. Last week we focused on derivatives. This week we're going to finish up derivatives and move on to integrals. And again, this should be mostly review for you. So I like to start every week with a challenge or a review. So this week what we're going to be doing is you're going to be combining the chain rule and the product rule, which we covered both of individually last week. So here are your challenge questions, or warm-up. Alright, so just a quick reminder, pause the video, work out these problems, and press play when you're ready to go again. Alright, so how are we going to do this one? Well, as I said, we have to combine the product rule and the chain rule. So the first thing we're going to do is take the derivative of log of 2x, and we're going to leave e to the x alone. Alright, well in the log of 2x in this part, our u is 2x. So du dx is 2. So when we take the derivative of log of 2x, just using the chain rule, first what we'll do is take the derivative of log, so that's 1 over u, so our u is 2x, so that's 1 over 2x, and then we're going to multiply by du dx, so that's our 2. And remember, we're just leaving e to the x alone over here. Okay, and then we're adding. Alright, now we're going to leave our log to the 2x alone, and we're going to take the derivative of e to the x. Well, the derivative of e to the x is just e to the x. Okay, so these 2's cancel out. And I like to simplify, so I'm going to pull out the e to the x. But that's just my personal preference. And whether you want to rearrange things or not really depends on what the next step in a problem is. So since this isn't part of a larger problem right now, it doesn't really matter. And when I do the chain rule, I normally don't use the u notation. It actually trips me up a little bit because I'm so used to doing it the shorthand ways. Okay, so there's that one. Let's do the next one. Alright, so the next one, so first we're going to take the derivative of the sine part. So in the sine part, the u is 2x. Oh, just like the last one. Alright, then we already know what du dx is. So that's 2. So when I take the derivative of sine of 2x, well, the derivative of sine of u is cosine of u. And u is 2x, so that's cosine of 2x. Okay, and then we're going to multiply by our du dx, that's the 2, and we're going to leave our cosine of x alone. And then we're going to add on, we're going to leave the sine of 2x alone. Then we take the derivative of cosine, which is minus sine. Okay, let's just clean this all up a little bit. Now this last one, you don't actually have to use the chain rule. You could multiply out x plus 2 squared, but just for illustration purposes, I'm going to do it with the chain rule. And also, I would point out multiplying things out when it's squared is no big deal. Multiplying it out when it's to the 5th power, you don't want to do that. You want to use the chain rule. Alright, so in this first one, when we take the derivative of this part, our u is x plus 2. That's your inside function. So then du dx is just 1. That's pretty simple. Alright, so when we take the derivative of u squared, that just gives us 2 times u. and u is x plus 2. And then we just have to multiply by 1. That's easy. Alright, then we multiply times log x because we're leaving that alone. Next, we're going to leave x plus 2 squared alone. And then we'll take the derivative of log x. So that's 1 over x. So I just want to clean this up a little bit. Okay, all done there. Still looks pretty messy. You could pull out the x plus 2, but I don't think it makes it that much cleaner. Okay, let's move on. And I just want to point out that I don't use the quotient rule. That's not something I ever bother to remember. If I see something like, for example, sine x over x plus 2, rather than using the quotient rule, I'm going to rewrite this as something that I can use as a combination of the chain rule and the product rule. So I would say x plus 2 to the minus 1 times sine x. Remember, something that's in the derivative is to the negative power. So you can do the chain rule on this part and then use the product rule with this part, and then you don't have to use the quotient rule. Let me know if you have any questions about that. Okay, but I don't want to spend too much more time on derivatives. So the last thing I want to talk about with regards to derivatives is the second derivative. Now, the second derivative is nothing too complicated. It just means you're taking the derivative twice. But in case you're rusty, let me remind you what that notation looks like. Alright, this notation means to take the second derivative. And all that means is that you take the derivative twice. Alright, and sometimes this is written other ways. Like sometimes you'll see it written as f double prime of x. But we'll talk about that more when we start doing differential equations. Because when you do differential equations, you really don't want to be using this notation all the time. It gets pretty cumbersome. Let's bring this back to talking about some physics concepts. So acceleration is the second derivative of position. So we can write that like that. So acceleration is the second derivative of position with respect to time. So that means if we write it out the long way, you can see how this is related to acceleration being the derivative of velocity. Alright, because this is velocity. So let's do an example with this in the physics context. So if our position is given like this, and I'm going to write out all my units just this one time. 3 meters. Alright, so this function gives our position as a function of time. And we want to find the acceleration. Alright, so the first derivative is the velocity. That gives us 5 meters per second. Minus, alright, then we have to bring down the 2. Okay, that's our acceleration. Now, that's our velocity. Now we're going to find our acceleration. So that's the second derivative with respect to time. And that just leaves us with minus 20 meters per second squared. Now I'm being really formal writing out these units. I won't do this all the time, and I don't expect you to do it all the time either. I'm going to give you a couple position functions, and then I'm going to ask you to find the acceleration as a function of time. So in this case, the example I did, the acceleration is just a constant number. That's not always the case, as I'm guessing several of you know. Alright, so I'm not actually writing the units on all these numbers here, like on this 3 or this 3 or that 3 or this 8. So I encourage you to be thinking about what the units should be on those numbers. But for now, what I want you to do is figure out what the acceleration is based on these position functions. So pause the video, try these out, and then press play when you're ready to go. Alright, so to find acceleration, all we need to do is take the derivative twice. So the first derivative, I'm doing the chain rule. I'm going to start doing it the shorthand way. So the derivative of the 3t is just a 3. The derivative of sine is cosine. And then we just leave our 3t alone. Okay, done there. Then we take the second derivative. We bring out a 3 again. 3 times 3 is 9. The derivative of cosine is minus sine. Remember, watch your signs. My students mess this up all the time. Well, and to be honest, so do I. Alright, there you go. That's the acceleration as a function of time. And remember, I'm not writing out all the units, so be thinking about what units should be there. Okay, this next one gets a little bit messier. Okay, we do the first derivative. We have to do the product rule on this one. So the first thing we're going to do is I'm just going to take the derivative of the e to the minus t part. So the u is minus t, so we just have to bring down a minus sign. And the e to the minus t stays the same. And then we leave our cosine alone. Then for the next one, we leave our 3e to the minus t alone. And the derivative of cosine is minus sine. To make the next step easier, I am going to consolidate this. So I'm going to pull out the minus 3e to the minus t. That's in both terms. Then I have the cosine and the sine. Okay, next step, let's take our second derivative. First thing, I'm just going to take the derivative of the exponential again. Same deal as last time. Our u is minus t, so I just have to pull out another minus sign. So minus times minus 3 is a positive 3. 3e to the minus t. Then we leave our cosine and sine alone. Alright, next up, product rule. So we're going to leave our minus 3e to the minus t alone. And then we're just going to take the derivative of the inside. So derivative of cosine t is minus sine t. The derivative of sine t is cosine t. And if we clean this up, what we end up with is that 6e to the minus t times sine t. Okay, that got a little messy, but it cleaned up nicely in the end. Last one, this one will be much cleaner. First derivative of position is just 3 plus 16t. Second derivative, (16). Okay, remember, think about what the unit should be because I'm not writing them all out right now. That's all we're doing with derivatives. Next up, we're going to move on to integrals. So, what is an integral? Just like we did with derivatives, we're going to look at this graphically. So if I have some function f of x, so if we're doing a definite integral, say we're integrating from this point A to this point B, what the integral is going to tell us is the area under this curve. And the way that we write that is the integral of f of x dx from A to B. This is a definite integral because it has starting points and ending points. And we'll talk more about the difference between definite and indefinite integrals later. The other way you can think about it is that you're doing little additions, and really it's just another way of saying the same thing. But it matters how you think about it depending on what problem you're doing. So you have some little length here, and you have the value of the function here. And really, you're adding up the value of the function times this little length dx, and you're doing that over every little speck of this line. So it's a way of doing addition when you have a continuously varying function. So part of this particular topic is what we read about in the first reading assignment, is how students think about derivatives. So I encourage you to talk about how you discuss integrals with your students in this week's reading discussion and in this week's problem solving discussion. There is a fair bit of overlap this time. And you can also just think about integrals as the opposite of derivatives. Let's bring physics back in. As before, we're just going to talk about position, velocity, and acceleration. So velocity is the integral of acceleration with respect to time. And position is the integral of velocity with respect to time. And in this case, I don't feel like thinking about area under the curve makes the most sense to me conceptually. You may differ, but I like to think of it more about, I know that the distance travels, if everything is constant, the distance traveled equals the velocity times time, but my velocity is varying. So I take the velocity at a little instant of time, add it up to the velocity another little instant of time. So thinking about it as addition works for me a little bit better in this case. So I want you to talk about pick one of the discussions and talk about how you explain integrals to your students. So we need to be able to do basic integrals. So let's review what some common integrals are. So we have the power rule again. So if you're integrating something that's x to some power, then you bump up the power on x and you divide by the new power. This is an indefinite integral because I didn't put boundaries on it. Whenever you do an indefinite integral, you have to add some arbitrary constant. And the reason that is, you can think about it in terms of derivatives, because if you take the derivative of a constant, you get 0. So based on what you're integrating, you never know if there should be a constant there or not. But when you're doing a physical situation, there are ways to figure that out. Do note that this doesn't work if n equals -1, because then you would be dividing by a 0. Let's do an example. This is pretty abstract looking, and I'm betting most of you are fine with it, but just to be on the safe side, let's do an example. Alright, we're integrating x to the 4th power. So we're going to bump up the power of 4 to 5, and we're going to divide by the 5. And we're going to add on that c. You always have to have that c. And you can always check that you did this correctly by taking the derivative. So if we were taking the derivative, you would bring down the 5. That would cancel out that 5 and bump this down to the 4th power, and the c would go to 0 because it's an arbitrary constant. Yay. Okay, next one you need to know. We need to know our trig functions. And remember, these are just, you're doing the opposite of when you're doing a derivative. So the integral of sine is minus cosine. Again, be careful with your signs. This is where my students mess up all the time. And I always have to stop and think a minute to make sure I'm not going to mess up. Okay, the integral of cosine is sine. Alright, and just like derivatives, the exponential is easy. So when you're doing the exponential, it's its own integral. But you still have to add that plus c. Okay, now what do you do if x is to the minus 1? Remember, x to the minus 1 is also 1 over x. You can write it either way, depends what you're doing. Well, that's just log. So those are some common integrals. There's one more integral that you don't see that often, and it's the hardest one to remember. But you don't have to memorize it. The ones on the last page I would probably memorize, but maybe not this one. The integral of log is x log x minus x. Don't forget your plus c. I know, it gets a bit repetitive to write the plus c, but it's important. And you can look up all sorts of integrals in integral tables, so you don't have to memorize a lot. And you can use crib sheets on exams. But just the ones that are pretty common, you'll memorize just because you use them all the time. Now I will give you a couple to try yourself. They should be pretty easy. Okay, so pause, work through these, and press play when you're ready to go. This first one, it's a power of x, bump up the power, and divide by your new power. Add c. Easy enough. This one, I'll write the integral of cosine is sine. The integral of sine is minus cosine. Plus c. Okay, last one. This one is just a constant. Technically, it is part of a power rule where x is to the 0 power. So you can think about it as 5 times x to the first power divided by 1. But you'll just remember, you have a constant, stick an x on it, and add c. Next up, we're going to pull back to kinematics. So again, we're talking about position, velocity, and acceleration. And what I'm going to have you do next, I hope you do with your students if you teach calculus-based physics. I always think the first time you do this, it's pretty exciting. So, say your acceleration is a constant value, and we represent it with the letter A. What I want you to do is find the velocity as a function of time and find position as a function of time. Okay, so pause, go for it, press play when you're ready. Okay, so velocity is the integral of acceleration. So that gives us a is a constant, so just multiply times t, our variable. Add a constant. I'm going to call our constant c1 this time. Alright, next up, our position is the integral of velocity. Okay, well, we just found velocity, so let's plug that in. And we get, okay, so we integrate AT, so we got to bump up the power on the t, divide by our new power, the 2. C1 is a constant, so just multiply that times the t. Then we have to add another constant. I'm going to call that C2. That's why I called this one C1, is because I knew I would have to have another constant. Now I want you to take a moment to think about what are these constants in this case. You can probably figure it out just by thinking about the kinematics equations that I'm sure you all know and love. So C1 is your initial velocity. So velocity is AT plus V naught. And C2 is your initial position, which is often defined to be 0. You know, it's nice to define your coordinate system conveniently. So your position as a function of time is 1/2 AT squared plus V naught t plus x naught. Okay, so we have our kinematics equations. The first time I learned this, I was so excited about it. And I hope at least some of your students get excited about it too. Obviously, I'm an exception because I'm a physics nerd. So the next thing you need to know to do lots of integrals is U substitution, which hopefully will look familiar to you. Substitution. So U substitution kind of reminds me of the chain rule. Well, in part because you're writing U's. And it confused some of my students because they'd be thinking about the chain rule when they should be thinking about U substitution, or the other way around. Let me know if any of you have problems with your students doing that also. So let's start off with an example. So U substitution and the chain rule do both have in common that they're about having functions inside of functions. So let's say we're integrating x plus 1 squared. And yes, you can do this just by multiplying out x plus 1 squared and avoid U substitution. But remember, if that x plus 1 is to the 5th power, you're not going to multiply it out. So let's just do our example. So our function inside a function is x plus 1. So if we were doing the chain rule, we would write something like du dx equals 1. But we're doing U substitution, so instead we're going to write du equals dx. And it just looks like you multiply the dx over there. And that's the way I remember to do it. But if we have any math majors in here, and I think we do, you probably know that mathematicians would get mad at me for talking about that. But I'm a physicist, and I'm going to do what I need to do. And we need to find whatever du is in our integral. That's easy in this case because du is just dx. So let's do our substitution. X plus 1 is u, so that's u squared. Dx, we have our dx, so we can just replace that with du. So we do our integral, bump up the power on the u cubed over 3. Add c. Always got to add that c. And then we go back and replace our u with our x plus 1. Okay, not too bad. So let me know if you actually need to use U substitution in your classes. I'm not sure at what level the APC exam is, for example. Okay, let's do another example that's a little bit more complicated. So now we're going to do the integral of sine 2x dx. Now our function that's inside a function is 2x. So u equals 2x. And du, the derivative of that is 2, so that's just 2 dx. So we need to find this 2 dx inside our integral. Well, the dx is there, but the 2 isn't. You can always put constants inside of integrals. So we're going to put a 2 inside of here. Okay, but really, we just multiplied by 2. We can't multiply by 2. We can only multiply by 1. So to cancel out that 2, we're going to stick a 1/2 on the outside of our integral. Now that's allowed. So you can put constants in, but you can't put in more x's. Like if your du said you needed another x that wasn't there, you can't put an x here and then an x out there. That's not allowed. Okay, so now we have our 2 dx, so we can do our substitution. So we have 1/2 our integral sine of u and our 2 dx, so that's du. Great, so now we can do our integral, and the integral of sine is minus cosine plus c, because we're doing indefinite integrals. All right, let's replace our u with our 2x. Okay, and that's it. Now I'm going to give you a few to try yourself. So we have e to the 3x power. We have x times the cosine of x squared. I don't have to write these parentheses, but I am for clarity that the x squared is inside the cosine. Now we have 3x plus 2 cubed. All right, try those out. So in this first one, 3x is our function inside a function. So u equals 3x, du equals 3 dx. We need to find this 3 in the dx. The dx is here, but the 3 is not. So I'm going to put a 3 in here and pull a 1/3 out here. Now we can do our substitution. 1/3 integral e to the u, and 3 dx becomes du. Well, now this is an easy integral. We just have 1/3 e to the u plus c. Then we just need to go back and do our substitution for our u. And you can always go back, if you're feeling a little mixed up, you can always go back and do the derivative of this and make sure you get what you were integrating. Then you know you did everything right. Okay, not too bad yet. All right, on our next one, our function inside a function is the x squared. So u equals x squared, and du, the derivative of x squared, is 2x, and we have a dx. Alrighty, so we need a 2x and a dx in here. We have an x, we have a dx. I'm going to have to add in that 2. And that means I have to put a 1/2 out here. Now remember, I need this x. There's an x there, so everything's okay. But if there wasn't an x, you cannot put in an x. You can only do that with constants. Okay, let's go ahead and do our substitution. So we have 1/2. Okay, we have our cosine. X squared is u. And we have 2x dx, that's our du. The integral of that is 1/2 sine u plus c. So that's 1/2 sine x squared plus c. Okay, great. Done. This one, okay, yes, you could multiply it out, but it's cubed. You don't want to do that. Better to do u substitution. So our function inside a function is 3x plus 2. And du is 3 dx. Sounds pretty easy. So we need the 3. We're going to divide by 3 outside. Let's do our substitution. 1/3 3x plus 2 is u, so we have u cubed. 3 dx is du. Okay, this is a pretty easy one. So we have 1/3 times u to the 4th over 4 plus c. So we get the 3 times 4, we get the 1/12th, u to the 4th, that's 3x plus 2 to the 4th power plus c. I know writing the c's feels kind of pointless, but it will matter when we get to a real physical situation with initial conditions. We'll get there. So the next thing I want to talk about is what you do when u substitution doesn't work. So there are actually a lot of techniques for doing integrals. But this isn't a calculus class, we're not going to go over all of them. So I want to make sure you all know how to use your integral tables. And I'll put a link to some integral tables I recommend. And also, if you bought the recommended book, the handbook, then that will also have a very thorough integral table in it. So let's just start with an example. Let's say we want to do the integral 4 divided by the square root of 9 minus x squared dx. Okay, so the first thing you'd say is, can I use u substitution? If you were going to use u substitution, what would you think your integral inside of an integral is? U equals 9 minus x squared. So our du would be minus 2x dx. Let's see if we can find the minus 2x dx. Well, there's a dx, obviously. And we can always put in the minus 2. But there's no x up here, and we cannot put in an x. That is not allowed. So u substitution does not work. What are we going to do? Yes, there are other methods besides using the integral table to do this, but we're not going to worry about it. So if I look up in an integral table, the one that I'll put a link to online looks like this. A squared minus x squared dx. Okay. Yeah, this is a 9 and this is an a. I apologize if they look a little bit too similar. So in the integral table I looked up online, a is used to represent a constant. A squared. Alright. 9 is a constant. This is a constant. Minus x squared. Alright, this one will work. And this integral table doesn't write the plus c's, so you just have to remember that yourself. Let's get our integral in the correct form. Okay, well, there's no 4 up here, so let's go ahead and pull the 4 out. And here I'm writing my 9, not an a. I apologize for that. Okay, now in this case, we see that our a, alright, so this is a squared down here. So what squared gets you 9? 3. So a is 3. So then we just need to use that. So the integral of this is the inverse sign. So this gets you 4 times what the integral table tells you. Inverse sine x divided by a. Well, we figured out our a is 3. And we have to remember to add our plus c. Okay, let me know if that makes sense. In your integral table, if you're using a different one than the one I found online, it may look a little bit different. Sometimes this wouldn't be a squared, it'd just be a. It depends, or they might use a different letter, but the idea is the same. So I will give you a few to try yourself. The ones I'm going to give you are definitely in the integral table online, and they should be in the handbook or the pocket book as well, but they might look a little bit different than what I'm going to show you today. I just wanted to use something that I know everyone has access to for today. Alright, so here are yours to try. Yes, that is an h after the tangent. That's tangent, or hyperbolic tangent. Alright, take a minute, try these out. So if I look in the integral one table online, this is what I find. Now this one I think you can do by using trig identities, but I just want to demonstrate how to do integral tables for now. So we've got to pull out our 3, okay, and here the a is what goes next to the x, our coefficient, so that's 2, so a equals 2. So what we get is 3 times x over 2 minus sine 2 times 2 is 4, divided by 4 times 2 is 8. Don't forget your plus c, and it doesn't matter if you put your plus c multiplied by the 3 or not. 3 times a constant is still an arbitrary constant. Alright, next up, hyperbolic tangent. So if I look in the table online, this is what I see. The integral of hyperbolic tangent, or tang, is 1 over a times the log of hyperbolic cosine, or cosh, or cosh, depending on who you're talking to. Okay. So all we have to do, there's no constant out front of this one, is figure out what 3 is. Alright, a equals 1 over 3. So our integral, 1 over a is 3. A times x is x over 3. That's it. After you add on your plus c. See, I almost forgot that time. Okay, so we're not quite done with integrals. We still need to talk about the difference between definite and indefinite integrals, and we also need to do integration by parts, but I don't want this video to run too long, so we'll cover those next week when we start off our introduction to differential equations. Alright, let me know how much of this was review for you, and if you have any questions, just post them in the problem solving discussion this week.